So we're going to talk about the laws of thermodynamics, but we kind of know already that objects are going to reach thermal equilibrium with their surroundings. And we'll talk about that in more detail. But Newton's law of cooling is the fact that the bigger the difference in temperature between the object and the surroundings, the faster the rate of cooling. So we're going to look at that exponential relationship there, because the rate of cooling of an object is proportional to the temperature difference between the object and the surroundings. So we're going to look at those rates and how that changes. So as an example here, let's say that Jim has the summer job and has to cook up a big pot of soup late at night just before closing time, so we have it for the next day. But he found that while refrigeration was necessary, the soup was too hot to be put directly into the fridge when it was ready. So the soup had just boiled at 100 degrees and the fridge was not powerful enough to accommodate a big pot of soup like that. It had to be at least 20 degrees before it went into the refrigerator. And so if you have heard this before, I guess I'll do a little bit of food safety here. You really shouldn't cook up a really big pot of soup and put it right in the refrigerator, a big pot of anything, because the center of it is just not going to be able to cool down enough for that food to be safe. So this is what's going on here. So he discovered that by cooling the pot in a sink full of cold water, keeping it running so that the temperature is roughly a constant 5 degrees Celsius. This is going to be our ambient temperature. And stirring it, he could bring the temperature of the soup to 60 degrees in 10 minutes. So that's kind of some data that we're going to work on. Remember, he's got to get it down to 20 degrees Celsius, but he knew that if he keeps stirring ambient surrounding temperature of 5 degrees Celsius, he could bring it the soup down to 60 degrees in 10 minutes. Now, this is not a linear relationship, so we're going to have to figure out what's going on here, what has to happen to get it down to 20 degrees. The question is, how long before closing time should the soup be ready so Jim can put it in the fridge to leave on time? So we're going to let the temperature at time t, so the big T is temperature, the little t is time, and this would be the temperature of the soup at time t. T sub 0 or T sub naught is the initial temperature of the soup, which in our case is 100 degrees Celsius. When we do other problems, our initial temperature could be whatever. For instance, I'll talk a little bit about how they use this for time of death calculation. So our initial temperature is what a body's initial temperature generally is, 98.6, somewhere around there. T sub A is the ambient temperature, so this would be the temperature of the water in the sink. For Jim, it was 5 degrees Celsius. And we're going to let the rate of the change of the temperature be proportional to the difference between the temperature of the soup and the ambient temperature. So this rate of change of the temperature based on the time is proportional to the temperature at time t minus the ambient temperature, the difference between those. And we're going to look at a solution here. So I'm cooling the soup down. So the temperature at time t minus the ambient temperature is greater than 0. We're trying to get it down to the ambient temperature because the soup is initially hotter. So the derivative should be negative. It's a decreasing function. So we're looking at the pattern here of we're going to set this equal rather than proportional. But we want to have a negative k because our soup is cooling down here. So we need to make this a positive quantity. So k, I have to put a negative out there. So I'm going to do a little bit of algebraic manipulation, divide both sides by this quantity, multiply by d sub t, the time. Integrate both sides. If you haven't taken calculus, it's not a huge deal, but 1 over x is the natural log of x. So you definitely want to find natural log on your calculator if you haven't already. And that's going to equal negative kt plus a c, a constant. Now, again, even if you haven't had calculus, I'm sure you've had, if we take applying e to both sides, e to the natural log gets rid of the natural log and it just becomes that. And then we're going to have e to the negative kt times e to the c. And so this c is going to end up actually being, I won't get into what's going on here, but at initial time, t is 0, so e is 1. So this c right here is going to be our initial temperature, T sub naught, minus our ambient temperature, and that will take the place of C. So we end up getting Newton's law of cooling here, where we can find that the temperature at time t, whatever we're interested in, like say I want it to be 20 degrees at a certain time, equals our ambient temperature, so for Jim that was the 5 degrees Celsius, plus the initial temperature, the soup was 100 degrees, minus the ambient times e to the negative kt. So this is your formula that you want to use. So let's go back and talk about this a little bit and put it in for Jim. So from the information we know that T sub naught is 100 degrees Celsius. The ambient was 5, that sink was 5 degrees. The difference between the initial temperature of the soup and the ambient temperature was 95. So what we're going to do is we're going to say, okay, the temperature at time t is equal to ambient plus the difference between initial minus the ambient times e to the negative kt. Now, we have some data. We also know that after 10 minutes, Jim can get that soup down to 60 degrees. So we're going to go ahead and plug this in to try to find this rate constant here, K. So we're going to plug in at time t, which, by the way, was 10 minutes. All right, so time t was 60 degrees, equals the ambient temperature of 5, plus the difference between an initial and ambient, times e minus 10, that's 10 minutes, times k. And by the way, this time really can be any unit you want it to be, just keep track of it. So if that's minutes, great. If it's seconds, you know, great. Just make sure you realize then the k would be the 1 over that time. Now, make sure that you can plug this into your calculator and solve for k. And when we do that, what's going to happen here is you are going to take 5, subtract it over there, you get 55. You're going to divide by 95. Okay. Now, you're going to have to take the natural log of both sides. So take the natural log of this, the natural log of this, and whatever you get there, the natural log is going to equal, and that'll get rid of that negative 10k, then you'll divide by that negative 10, and this is where you're going to get that k from. So I think maybe the next slide goes through that. No, it doesn't. Okay. So just make sure, coming back here, that you can get 0.054 when you do this calculation. Again, you're going to subtract the 5 over, divide the 95. Then you're going to take the natural log of both sides. So that'll be 55 divided by 95 equals the natural log of e to the negative 10k. So when you hit that natural log of that, you get whatever number there. I don't have a calculator in front of me. And then that'll get rid of that, and so it'll be equal negative 10k. You take whatever you get here, divide it by negative 10, and then you should get your k there. Okay? So, because we got that k, we can come over here, put that k in, and we have an equation that's going to help us solve for Jim. So, what's Jim going to do down here? I figured it out. I said, okay, so Jim needs to have the soup at 20 degrees. Okay, so that's the temperature at time t. He doesn't know how long that's going to take according to the rate, though. The rate constant is 0.054. So I'm going to plug that in. I'm going to go solve for time. And so again, you're going to subtract the 5, divide by the 95, take the natural log of both sides. In this case, you're going to divide by negative 0.054, and you're going to solve for time. So you should get, when you calculate that, 34.18 minutes. So basically what that means is that Jim's going to have that soup ready 34 or so minutes prior to the cooling process. Put the soup in the sink, start stirring it, leaving the water running. We are making some assumptions here. What if the water in the sink was not running? Well, then the ambient temperature is not constant, and that changes our assumptions. So we have to make some assumptions with this. If the soup wasn't stirred occasionally, you have to keep things constant in your constants. Otherwise, our assumptions are not going to work. They use this for time of death calculations. And how would they use that for time of death calculations? Well, we're going to take the temperature of the body, the dead body, right? We're going to look at the ambient temperature. So maybe there's, somebody dies in an apartment and the temperature of the apartment is 70 degrees. We're going to take the initial temperature of the body, which for most people is 98, around 98, minus the ambient temperature. We have a K constant for things like dead bodies, and we can find the time here, the time of that since the body has started to cool. So we can find that time and say, okay, well, that time is maybe 6 hours. So if it's 9 o'clock in the morning, go back. And you can see approximate time of death. So we'll look at those problems as well.